guess everyone can hear me okay? Okay, I'm Mike Stoner. Some of you may remember me from the Propel with OpenCL talk yesterday, or I've noticed you may also know me from the page which has my picture on it for some reason. But I think there are only a couple other people with pictures up there. But I'm actually presenting with Sonal here and Robert. So we're all from Intel in a couple different organizations. But we have some data on Opencl 2.0 in particular. Let me skip through these slides here. Some acknowledgments. Yesterday we talked about the fundamentals of shared virtual memory. Today we have some performance data and insights into how we can actually apply this to some code, which Sonal and I will be talking about. And then in the second half, Robert will be stepping in to talk about the device side and queue and some examples we can show you there. So just skipping through a lot of the fundamentals, but a quick summary here. With shared virtual memory, we can now pass host-allocated CPU, host-allocated pointers directly to the GPU. So on the GPU side, or any device really, we can now navigate through memory much easier than we could before, where we had to encapsulate all of our memory as a CL-mem object using the CL create buffer. So this is a diagram that's actually taken from a sample that we have out on the Intel Developer Zone network. It's just called SVM Basic. It's kind of a contrived example, just some arbitrary buffer interactions, but it sets up this buffer that has pointers, contains pointers to not only itself with the internal portion of the structure there, but it can also point to another SVM buffer, and then likewise that could contain pointers to additional SVM buffers and so forth. So it provides a lot more flexibility than we had with OpenCL 1.2. So the question there is, well, what kind of algorithm can take advantage of this? We were looking for algorithms that have these complex data structures that do pointer dereferences, but also have an inherent large amount of parallelism so that we can launch enough threads to keep the GPU busy. I'm kind of curious, other than the group that just was up here, has anyone experimented with shared virtual memory or found that type of algorithm that took good advantage of it? Did you?
Well, I'm only using them so that I don't have to transfer buffer to my device.
Okay.
The performance penalty, to my surprise, is only like 8%, which isn't bad.
Okay, well that's one possible usage, is to eliminate buffer copies, but in many cases we were already able to do that with OpenCL 1.2 and the buffer copy optimization, which we talked about a little bit yesterday, and that's along the lines of what the group from Northeastern did on those kernels, but those are on AMD hardware, so it's a little bit different architecture there. But okay, so I'm going to move forward. I've got this example that some of our developers found. It's actually from the University of North Carolina, but it's called crowd simulation, and visually it's like you have these 4 marching bands that are all starting in different corners of the screen, and as you progress through the simulation, you call the kernel repeatedly through a number of frames, and each quote-unquote marching band tries to move from one corner of the screen to the other. So what that looks like is just, I couldn't show a demo here, but just wanted to show a succession of screenshots. They kind of collide into each other and have some cool-looking screenshots along the way. Eventually, it's kind of fun just to watch them bounce off each other and find their way to their new home. They find some order on the other side of the screen eventually. And what's happening here is each thread, or each agent, is represented by a thread. So you can launch as many agents as you want, and you can end up with however many thousands of agents that this supports. And each agent has some complex data structures associated with it. With each pass of the simulation, it's building a new agent tree to figure out which agents are close to me that I have to worry about banging into, and I have to kind of navigate around and find my way to the other side. So there's a lot happening there. And this is an example, just a snippet of code here to illustrate the type of access that we can now do because we have SVM that would be very difficult without SVM. So we're passing in this agent data structure which contains pointers to other data structures, in particular the Orca lines array. So we can take our global ID and figure out which agent we are, and then we can go further to find the Orca lines pointer there, and then we can dereference that a number of times. So without SVM, we would have to roll up each one of those pointers into its own CLMEM object, which would be very tedious as a programmer. Right. Well, one of the things that this sample highlights is we didn't have to change the data structure largely. There's actually, this hasn't quite been published yet. We've got the code that looks fairly ready to be published, and we've got an article that our developer wrote that outlines it in a lot of detail. But one of the things he tries to highlight is that he didn't have to change the code drastically. So you're right, there's other ways you can do it. So you're probably wondering about performance. Well, we've got some data points here. There's 3 different variants of the algorithm that we're showing. So the blue lines are the reference code that we started with, which was just single-threaded, so it's kind of a naive implementation, running the original C code. And the red is an OpenCL version, but running on the CPU. So this is taking advantage of the multi-core capabilities of the CPU. In this case, this was a dual-core machine. So with hyperthreading, we've got 4 virtual cores or 4 execution contexts, and it takes good advantage of that to get an increased frames per second over the C reference code. I should note this is a log scale, so I wanted to be able to show as we increase the number of agents that we still have some clarity over here on the right side with the log scale of the differences between the implementations. But finally, the green lines there are representing the SVM version, which runs on the GPU. You can see it takes till we get a decent number of agents, till we get enough threads to have enough parallelism to see the advantages of that. But when we get above about 20,000 threads, then we start to see about 1.2x speed up compared to the OpenCL CPU. A question here?
So is the CPU parallelized? I mean, I assume it is.
Right, so I was just trying to articulate was that the OpenCL CPU version takes advantage of the multi-core, so it's yeah, yeah. The C reference is not.
It's not single-threaded.
Right. So that's why I said it's a naive, more naive implementation. So I think.
Trivially parallel, if you run more agents, you use more of the CPU, or just one CPU core.
Right, you can see very distinctly with the reference version, it just uses 1 core, pretty much pegged, and then when you run the OpenCL CPU version with enough agents, then you see consistently 100% utilization across the system.
Oh, I think
That's a good question. I mean, I know it takes time to grasp a chart like this, so thank you for the question. Probably clarified for a lot of people. But one thing I want to note is this SVM version was using coarse-grained, and we also tried a fine-grained version. There was a question yesterday about the performance implications of supporting fine-grained. The fine-grained was a little bit slower. In this case, we didn't really need fine-grained because we're just doing all the work on the GPU. We're not trying to do parallel work on the CPU. But in general, the fine-grained accesses might take 10% more time. So it's not something you should just use automatically. You have to think, is there a good reason for me to be using fine-grained versus coarse-grained? And another benefit is if we use fine-grained, we can run in a heterogeneous mode or this hybrid mode where we launch threads on the CPU and the GPU at the same time. And I couldn't show performance data here because it wasn't fully baked at this point. But we do have a version of that, and I think we saw that we did get improvements from the hybrid version. So were there any questions about this before we moved along? No, maybe we'll hire an intern to work on that this summer. Okay, I think I probably used up most of my time, so I'm going to skip past this next slide. Perhaps we can chat more afterward, but Sonal has some data on Cyberlink to talk about here.
Hello, everyone. My name is Sonal, and is it on? Can you hear me? Okay. Hello, everyone. My name is Sonal, and me and my colleague, we work with Cyberlink, and we do Opencl integration for 2 of their products, which is Cyberlink Photodirector and Power-Director. Power-Director is a video editing software, and Photodirector is a photo editing software, and Cyberlink is a multimedia software company. So the last project that we worked on was doing SVM enabling for Power-Director, and we did like SVM enabling for many of their effects here. I think I want to share. Yeah. So we did like a total of like around 40 effects, and this performance that you see here is on Intel 5th generation processors, and on your left-hand side, this shows the production time in seconds, and this performance is taken at the app level, so it's like whole workload we are calculating here. We have like around 30 effects here which are showing positive performance, and the first bar is the CPU, and we are showing the performance of CPU multi-threaded code, and the next is Opencl 1.2. Almost like about 60% of the effects here use image objects. The rest of them use buffer objects. And the third bar is Opencl 2.0, which uses SVM, coarse-grained buffers. On the secondary axis there, it shows the percentage increase, and you can see the orange line, which shows the performance increase in increasing order. So all these effects are included in the product, and this will be released in this month. And we also have another product, Photodirector, which we are working with, whom we are working with, and we have around like 6 effects which are SVM enabled. Apart from these, I would still like to highlight that we had around, apart from these, we had like 5 effects which had like 0% increase, and there was some like around another 5 effects where we saw percentage decrease. And there are many factors I would like to highlight that are dependent on performance, and it could be the type of objects you're using, like is it image object or buffers, the memory operations, and the complexity of the algorithms, and the impact on their kernel time. So yes, so this is the data that I have from Cyberlink showing all the effects which shows performance with SVM coarse-grained buffers. And yeah, I'll hand it over back to Mike. Do you want to summarize?
Yeah, I think there's a summary slide. So yeah, just to summarize, we're curious, again, if you have experimented with SVM, or if you can think of those kinds of algorithms that have the complex data structures but still have the parallelism. Inherently, our team works a lot on the media applications, like we work with Adobe and Cyberlink and ArcSoft and others. So those data structures are pretty simple. They're just media buffers, they're images, pixel-based frames. And in this case, we get benefits from saving the memory copies, but we had really no instances of kernels where they were doing pointer accesses or anything where they were navigating through virtual memory. So we're curious to know if you have any other ideas about that. And check out the samples. We have the SVM basic that's already up there, and also there's a nice SVM overview that one of our developers wrote, and hopefully the crowd simulation will be up there soon. But going to turn it over to Robert here for the device side and queue. Thank you.
Right. Hi, my name is Robert Ioffe. I'm a technical consulting engineer for Opencl at Intel. And before I turned consultant, I was prototyping enqueue kernel functionality for Opencl 2.0. So I'll skip the definitions of device-side enqueue. So we covered it yesterday. And we also showed this kind of like a simple example of a Sierpinski carpet. It's a nice toy example that I used throughout my life to test various graphical applications. So, and also our driver team is in Poland, so I thought that would be a nice thing to port this. And they actually implemented the scheduler for device-side enqueue. So the Sierpinski carpet is a very simple thing. Like, you divide the square into 9 subsquares. You paint the middle one black, and then you continue to apply the same recursive procedure to the remaining 8 squares, and so you will get this nice picture. So this is Sierpinski carpet in Opencl. If you just like straightforwardly translate the algorithm into Opencl 2.0, what will happen is you can see here we are painting the middle square black, right? And the rest of the squares are painted white. And then you do the if you calculate these numbers, like we do 8 self-enqueues, and the way you do it is like you do enqueue kernel. This is your ND range, which is now 1/3. Actually, it's like 1/9 of the size, right? It's 1/3, 1/3. And you have a block with a Sierpinski carpet function inside it, right? So it's very trivial. Easy to translate your recursive algorithm into implementation. And this is the result. Very beautiful. And the cool thing is on 2K by 2K image, we can handle about 300,000 enqueues. Right, so the question that you may ask is like, well, I mean, it's all cool, like, is it performant? Well, it's not, right? So the recursive version of the algorithm takes more than 2 seconds to complete, right, on GT2 graphics. Right, so you are better off writing the iterative version. So if you go to Wikipedia and you look for iterative version of Sierpinski, so you can also implement it in Opencl, right? So and for every pixel, you just like run a little loop, and that takes 11 milliseconds on a 2K by 2K image, right? So what's to do? What you can do is you can combine the iterative and the recursive algorithms together, and so you have kind of like a hybrid version of it, and the mixed version will have approximately like a 5% increase in performance for a 2K by 2K image. Performance improves as you go to bigger images, right? So you get about 15% performance improvement for like 6.5K by 6.5K image, and about 23% performance increase for like a huge 20K by 20K image, right? So enqueue kernel will help you if you use it properly. So use it properly. Okay, so now for a more serious algorithm, right? So today, actually, it's not today. This year, we mark 55 years of invention of a Quicksort algorithm, right? So, and the GPU-Quicksort, it's kind of like a next iteration of this, right? So the GPU-Quicksort algorithm was invented by 2 researchers at in Sweden, and I think I'm running out of time, right? So, it's a 2-phase algorithm, and it's not recursive as the name would suggest. It's actually iterative algorithm, right? And it uses 2 phases. So it uses 2 big kernels. Like one is called like GQ-sort kernel, the other an LQ-sort kernel. So you iterate in the first phase of the algorithm, and you kind of like split things into smaller pieces, and then each of the smaller pieces you can sort on the work group, and that's called like a local quicksort. Right, so you can read it. I have like if you search GPU-Quicksort in OpenCL, you can read details of the algorithm implementation in Opencl 2.0. Right, so what we did in Opencl 2.0 is we have these workgroup scan functions in Q kernel, and so I first implemented the GPU-Quicksort in Opencl 1.2 and then ported it to 2.0 to see what performance we can gain, and also like how it would simplify the code. So we introduced this thing called relauncher kernel, and you can see from the diagram like below. Like, so what we do is like we launch the relauncher kernel, and that thing then iterates. So the control passes between relauncher and GQsort kernel iteratively. So you loop around like 40 to 50 times there, and then finally you go into LQsort kernel. And performance from workgroup scan functions is you get about like 8% performance increase from our optimized workgroup functions, and also your code side reduces dramatically from like if you were to implement a scan algorithm, let's say like from a Blalock paper, and we take advantage of the in Q kernels, and what you get is the 42 to 62% faster performance on HD graphics 5500, which is like a GT2 with 24 EU cores, right? So this graph summarizes performance improvements. So what I show here is in yellow we have a parallel CPU quicksort running on 4 threads of our Broadwell systems, right? So either this is the on the left-hand side is the GT2 system with 24 EUs. On the right-hand side, we have a GT3 system, which you can buy right now for about $400, right? So you can get yourself a nice GT3 Broadwell. And so the yellow line shows the speedups compared to standard library sort routine, right, of the parallel CPU quicksort. So on 4 CPU threads, you get up to like 3.5x performance increases. And then the red line shows the GPU quicksort in Opencl 1.2, and the green line shows GPU quicksort in 2.0. And what's cool about this graph is that for image sizes from like 1 million, for array sizes from 1 million to 67 million elements, GPU quicksort in Opencl 2.0 consistently outperforms your CPU, right? And well, on GT2, the picture is a little bit muddled. Like you start outperforming CPU at around 32 million elements, 33 million elements. All right, so I think that's it. Any questions? Right. What I show is the y-axis is speedups compared to STD sort. Right. Right. Sorry. Right. Radix sort beats us hands down. I mean, there is no competition with like Radix sort, right? Radix sort will be at like here it would be like 7 to 11 times faster than the. Oh, I see. Well. Right. No, I mean the point was to actually like take the algorithm, and I mean we're actually comparing the algorithm to itself, right? Like, oh, I see, got it. Yeah, but what we show though is that you can port like both recursive and iterative algorithms, right, to the GPU, and in fact it's very easy to do, right, and you and obviously like, sort is still kind of like a toy example, right, but you can do more serious algorithms, right, and we have a very performant runtime to so yeah, so if you guys want to start developing for Opencl 2.0, I think like for about like $400, you can buy yourself a small nuke box from Intel and start developing right now, right? All right, thanks.
Thank you. So let's thank our speakers. Thank you very much.